Hello, my name is Brenton Ashworth. I work for Cognitect, formerly Relevance, and this talk is about web applications. Is there a ring? Web applications in Clojure and ClojureScript with Pedestal. I apologize for the really long title and the ambiguity of the title. When I submitted this talk, I wasn't quite sure where Pedestal would be, and it's changed quite a lot since I submitted the talk. So just to make it clear where we're going, Pedestal has two parts. It has a service part and a client part. During this talk, we're going to focus on the client side of Pedestal. And it's designed to build a certain kind of application. We're going to take a look at the kind of application that it will help you build. And we're going to look at an example application that we built for a client. And then after seeing that and having a good example in our heads, we'll take a look at how we use Pedestal to build that example. And then we're going to take a look at the future. There are a lot of interesting things happening right now, and we're trying to incorporate a lot of new ideas into Pedestal. So if I could pick one word to describe the kind of application that Pedestal is designed to help you build, it would be interactive applications. And specifically, this definition that you see up here, this partial definition, applications which require that there be a continuous two-way transfer of information. A lot of the applications that we've worked on at Relevance in the last 2 years that I've been there have been this kind of application, and we found that we need something to help us out. If you decide to make this kind of application, there's a lot of implications for how you need to think about developing it and even the artifacts that you'll create. We can no longer just assume that the person sitting in front of the screen using the application is going to be the only source of events that we need to respond to or react to in the user interface. We receive inputs and events from multiple sources, and we need to somehow coordinate all this information into a coherent picture and display it reasonably to the user. And this requires that we do coordination now on the client that we used to just do on the server. And so we need something to help us out there. When we do this on the server, we have a database, and we usually do all our coordination there. And when we have a lot of state and a lot of events coming into the client, we need something to kind of play that role. These applications don't really have like a clear page reload boundary, so they run for a long time. That means they're usually larger and large from a code perspective. They do more, and it's a lot more code. So we need to actually apply real engineering effort into making these applications to make sure that they run well and don't die on us. So why in the world are we creating something new? We need something besides just a language. Languages are important, and we like ClojureScript for these kinds of applications. But in any endeavor, we usually use libraries to help us out. And we think that something is needed here, and later in the talk, you'll see some of the things that I think we need and how we implement those in Pedestal. Also, there are a lot of existing libraries that we could use, but I think that from our standpoint, they either aren't well suited for building this kind of application, or they rely heavily on mutation, and they have a lot of object-oriented concepts, which I think unnecessarily complicate things. So we want to build something that is more functional and will allow us to program in the way that we're used to in Clojure, even when we're in the browser and making large applications in the browser. So the first thing we're going to do is take a look at an example application, something that we built for a client. We had a client that came to us and asked us to build a way to visualize their sales funnel. And they wanted to see in near real time how people are progressing through the funnel, and how, and if there's any problems, how they would be able to see how they could deal with those problems in real time. And the system needs to support receiving about 1,000 events per second from the system that it lives within, and even though it's getting 1,000 events per second, it's updating the browser about twice a second. So this is a very high-level overview of the architecture of the whole system. I just wanted us to see how the thing that I'm going to show you fits into the rest. We have a system that we deployed on AWS. If you go from left to right, we have collectors, which are polling or having data pushed to them. They're putting that data on a queue. We have aggregators pulling data off the queue and doing some processing and sticking that data into Datomic. And then we have an analyzer, which is being notified whenever new data arrives in Datomic, and then pulling the new data out, rolling it up, and sending updates to the browser twice a second. And so I'm going to show you a screenshot of the application and explain what all the pieces are, and then we're going to run it. So hopefully you can see that. And what we have is we have the states that people could be in. And each state, the size of the circle representing the state, represents the number of people in the state. Around each one, we have a donut that tells us how many people are instantaneously arriving in the state versus leaving the state. The paths tell us how people traverse between states, and the bubbles going along the path are telling us how many people right now are traveling between the states. And then paths on the top above the circles represent forward motion through the states, and then paths on the bottom represent backward motion. And if you look over, there's one state that's got like a little bit of blood dripping out of it, and that represents people dropping out of that state. So we've also got some charts that show us the number of users currently in the funnel and how much inventory we're selling and errors. And then at the bottom, we have the history of each state. So I'm going to show you two versions of this, one that works and one that doesn't work so well. So we're feeding data into the visualization, and we're feeding data once every 5 seconds to start with, and then we're going to ramp up to once or twice a second. So you can kind of see how it works as we progress. So it will order the states as data arrives in the way that makes the most sense. This is a pretty simple flow. Everybody's just moving through the states in order. And we can see that the thicknesses of the lines represent how many people are actually traveling between each state. And what we're going to see here is that if you can see the labels, the shipping state is actually getting larger. It's getting clogged. And we can see that there's a big blue donut and a little bit of orange. That means that there's a lot of people arriving in that state and not a lot of people leaving. And so maybe the person watching this would get on the phone and somebody would push some buttons and somehow solve this problem. We can also see that that sales is kind of suffering up there. We've dropped off because not a lot of people are making it clear through to the confirmation state. And now we've added some new ways to traverse through the states. People can skip over shipping now. So anyway, that's just a simulation to show you how it works. Don't be afraid of all those errors up there. It's just a simulation. Normally, that much wouldn't be going wrong. So I want to show you one version of this that doesn't work so well, and we'll see if we can see how it doesn't work. So it's the same exact code. It's just running in a different way. And we're going to start sending messages once every 5 seconds and then ramp up to twice a second. Can you see this, by the way? Yeah, OK. So what you see here is there's a pretty significant pause. And that pause is happening whenever we get an update and we have to process the data and figure out what to do with it. So I don't know how many of you have run into this kind of problem when you have a lot of animations in the browser and you're trying to do other work. It can be kind of tough to figure out how to solve it, and sometimes we have to resort to breaking up our code into all these pieces with timeouts between them in order to make this run smoothly. So that's the demo. So this is what we're trying to build, and there's really two hard problems here. How do we draw all this stuff? That's hard, and Pedestal doesn't help you with that. And then how do we control it? There's a lot of state that we're getting in the browser, a lot of messages, and there's a lot of things to control on the screen, even what's visible on the screen. And how do we do that? And that's the part that Pedestal helps us with. So what we did on this project is we divided the work into these two main categories. We used Raphael for the animations, and we used high charts for some of the charts. And we created widgets. We wrapped these things into self-contained pieces of code that we could add to the page and remove. And each one had a simple API, so we could send data to it, control it. For example, we could tell the big chart, make this state a certain size or this path a certain size. And that, all that code was actually written in JavaScript. We had people working on this project with different skill sets, and so the people that were some of the people helping with the widgets didn't know ClojureScript, so we just wrote these in JavaScript. So we have widgets, and they can draw the things that we want to draw. But none of these things have any kind of application state in them. They just draw things on the screen. So we need to be able to control them. We need to be able to determine when these things should be displayed, and that's what Pedestal helps us do. So Pedestal, at least in the context of this project, provides at least 4 things that helped us out. It provides a clear separation of concerns. It provides an information model. We're going to look at these one at a time. It provides an information model, a state transition model, and data flow. So what do we mean by separation of concerns? The thing that Pedestal does that I think is very helpful is that it clearly separates these 3 things: rendering from your information model and logic, and services. And what I mean here by services is the part of your application that does communication with the back end. So this might be the part that's got like an SSE connection, or a WebSockets, or is making HTTP requests to the back end. We want to isolate that because it can be very complex, and if you let that get intermixed with everything else, you're going to have problems. And then the same with rendering. We want to keep that isolated as much as possible. These 2 places, rendering and services, this is where all the complexity of programming in the browser exists. So we want to keep these things, keep those isolated. And then in our information model and logic, that is where all the application logic for our application lives. That's where all the state lives. And that's really very simple. It's data transformation. And this is the kind of thing that Clojure is really good at. We can run this code in the browser. We can run it in Clojure to test it. That makes testing very easy. So anyway, how do we separate these things? We separate them with messages and queues. So there's no way to, well, you can probably call across them, but if you want to use Pedestal, you communicate between these parts by sending messages, and you send messages on queues. We don't make direct function calls across these boundaries. So messages just give us a way to communicate without making function calls, and then queues sever the direct connections. So even if we didn't have queues but we had messages, we'd still be determining when things run. Queues give us the ability to kind of step away from that. And these queues are not real queues. They're JavaScript style queues. They're kind of simulated queues, basically an array and asynchronous processing of that array. Queues also give us the ability to independently process the data on the queue. So we can take a look at our application, and if the queue backs up, we can decide we're going to start dropping stuff, or we can maybe compact things. And it's very nice to have them. I just wanted to show you an example of the kinds of messages that we would use. I'm not going to go into the details of these messages, but I just wanted to give you an idea of what they look like. The top message is the kind of thing that we would send into our application, and the bottom 2 are the kinds of things that might go out to the renderer. And these would be mapped to functions which perform some small change in what we're rendering. And so in this application, we used widgets. The functions that receive these messages would maybe make an API call to a widget to make a small change. Notice that there is a similarity between these messages, even though they're slightly different. They all have an operation, something we want to do. They have a target, the thing that we want to do it to, and then they have arguments. And in the future, this is actually going to get standardized a bit. So next, we'll look at the fact that Pedestal has an information model. And what I mean by this specifically is that we have a standard way to organize and store data. If you didn't have this, you could store data however you'd like, or organize your data however you'd like. But if you do that, you can't really leverage that. You can't build things on top of it. So having some kind of standard helps us out. It's kind of like in a database. You have schemas, and you talk about types, and that allows the database to do things more efficiently. So the way that we store data is in a tree, and you can just think of this as nested maps. That tree contains the basis information that we might receive from other sources that talk about things that we know. These are the facts that we have learned about. We have derived information, things that we derive from the basis information, and we have some information that supports the UI. So that's what we put in our data model or our information model. So this is what it might look like. This is a representation of that. It's a tree. We see the nodes, but we don't really see the values in the tree. The thing that this allows us to do is talk about nodes in the tree using paths. So the one that you see on the bottom there is a path to a specific node, and we might use that to say, I want to update that subtree. And the top message has a wildcard in it. We might use that to say that we would like to be notified if one of the children of the devices node is changed. These are just the way that we can refer to nodes in the tree. And this is an example of one thing that we can have if we assume that there's a certain structure to our data. So another thing that we have are state transitions, a state transition model. And what I mean by this is that there's some way to have an orderly succession of states. Our application state is stored in one big tree. And we want to know that when there's an input, we're going to have a new tree, a new state. And we want to know that we're progressing between states in an orderly way. We're not updating things in a random fashion or out from under us. We also want to be able to associate cause and effect. So something happened. We now have a new state. I want to be able to associate those two things. Here's the cause. Here's the message that came in. Here's the new state that produced. That's extremely valuable for testing. So if you've written applications in ClojureScript, you may have used an atom for this type of thing. It's well suited for this, and some of the implementations of our transition model use an atom. If you're not familiar with Clojure, an atom is a reference type. It allows you to deref it and get a value, an immutable value, and you can send functions to it, perform state transitions. Those are atomic state transitions. You can also add a watcher to the atom, and then the watcher function will be called whenever the atom changes and get the old and new value. And so we can use this to store state and be notified when that state changes. But one of the problems that you run into is you start to ask yourself, how many atoms do I need to use? It's nice to have everything in one atom because you have all your state there and you have consistent updates. But as that data gets larger and larger and larger, it's harder to tell what you've changed. So if you change one thing, you have a lot of data, now you have to figure out where's that one thing that I changed. So we would like to have the best of both worlds, and that's what Pedestal gives us. It gives us a way to consistently move between states, and we have fine-grained change reporting. So you can keep all your state in one thing, and you can watch for specific parts of that thing and be notified when that part changes. So data flow is another thing that Pedestal provides. It allows us to disconnect functions from how they're executed. And what this means is that we can declaratively say, here are the inputs to this function, and here's what should happen with the output. And then the engine that's running our application can decide when that function needs to be run. It will do that based on what has changed in the data. So we specify declaratively the positions in the data that we're actually watching, and when those positions change, when those nodes change, the function is called, and we get an update. So this allows us to atomically propagate changes through automatically propagate changes through our data model. This is all based on the data model, so we're not actually tying together function inputs and outputs. We change the data model, we call a function, that updates the data model, and then another function may be called if it's watching the output of the previous function. So this is all centered around the data model itself. It allows us to avoid writing explicit pub/sub code or big hairy conditionals. So some of the advantages of data flow is that it's a great way to encode the dependencies between data in UIs, in UI applications. These can be quite complex, something like I click a button, I want a menu to be a menu item to be disabled, and I want maybe some other menu items to show up. We can do all that with data flow, and it's actually a nice way to do it. It also promotes adding code rather than updating code, which I think is nice. You usually write very small focused functions that are part of the data flow, and if you need to do something new, instead of finding the conditional that you need to update and going in and updating some big nasty confusing thing, you can add a new function to the data flow. So what we're going to do now is walk through how the data flow would actually work to give you a better idea of how this works. In the upper left-hand corner, we have our view. Something's going to happen in the view to generate an event, and then the callback for that event is going to transform that event into a message and put it on a queue. So that green arrow is a message on a queue. And then what we do is we find a function that handles that particular message. That function runs, and it updates a part of our subtree. And even though it operates on a specific subtree, the thing that it changes might just be the phone node of that selected subtree. And then the visible node, the blue one down at the bottom, it depends on selected. So if that selected changes, we want the visible subtree to change. So the data flow engine will know that that changed and know that that function depends on it. And that function has two inputs. It cares about both the selected subtree and the device's subtree. And those will be passed into this function. It will produce a new value for the visible subtree. And what that will do is update the review node, and so on. We update the order node. And then finally, what we end up with is these are the things in the tree that we actually changed. And in between each of these steps, we generate a change report that tells us what actually changed. At the end of this process, we would have something that might look like this. These are the things that actually changed in the tree, and then we can use that to match patterns later on and find functions that may care about that. Or when we're finished with the complete state transition, we would get this report out, and we can do something with it. So another way to look at this is to think about what a round trip looks like. If something happens in the view, how does that work its way through the system and actually update the view? So again, we have an event, and we have a message on a queue. And then this green box represents finding a function to handle that message. And then the black arrow there is basically taking the return value of that function that we found and applying it or using that to replace some part of our information model. And then the info model has changed. So we get a change report, which is the orange dotted line there. And the same thing, we find a function that cares about that. The return value updates the data model. And these run until we're finished. And then when we're finished, we have a change report coming out the other side, and we find a function that is going to generate the data that we're going to send up for rendering. And we have a renderer. That guy is going to find a function that handles each message and make a change to the view. So that might be like a fine-grained change to the DOM, or it might be a call to an API. So in this case, we're controlling widgets, so we're calling some function on our widget API. So the reason why in the example that I showed you, there were two versions of the application, one of them that didn't work so well and one that did. And the reason why the one that did work so well worked is because we've separated rendering from all of our application logic. We can run them in different places. So I can run all of the application logic in the data flow. I can run it in Clojure for testing. I can run it in a web worker. And we already have a way to communicate across the boundary between the web worker thread and the main JavaScript thread. And so that's how that application runs. Everything about the application runs in a web worker, and rendering happens on the main JavaScript thread. And so I have to say it was pretty nice being able to program in the browser with real parallelism. So that's how that works. That's at least an overview of how it works. So then while we were working on this, I think when this project started, the project that we did for the client, that was about the exact same time that CoreAsync was started. And it finished about the time when we finished this project. And if you're ever working on something and Rich Hickey starts working on something related to what you're doing, you should probably just wait and see how that's going to affect what you're doing, because it can disrupt you. So we have all these things. How many people here went to Rich's talk and know what CoreAsync is? Okay, so almost everybody. CoreAsync, I'm not going to really cover all of the things that CoreAsync gives you, but basically it provides channels. So these are more like real queues, not like the fake ones that we're using. It allows us in the browser to program as if we had threads. So we can have real processes that are communicating with each other. And we can block, which is amazing in the browser. You can actually sit there, block on a channel, and it's not going to keep the rest of your code from running. And so there are some huge advantages here. And we want to have these advantages as well as some of the ones that we already have in Pedestal. So if you think about some of the diagrams that I showed you, there's a couple problems in those diagrams, a couple problems that we have in Pedestal right now. One of them is that if you look at the way we process messages, going from some kind of event happening or something changing to some value that might change our information model or affect something else, we have this basic pattern that we go through. We have a change come in, some sort of novelty, either a change to our info model or a new message. So it's something new. And then we have a way to take a map of patterns to functions and find a function that handles one of those changes or cares about one of those changes. We call that function, and then we get something, we get a return value, or we get a message that we put on some kind of a queue. And so we're doing things in a couple of different ways which could be unified. And the way that we plan to unify them with CoreAsync is to think about having two different kinds of channels. A channel that we'll call an inform channel that carries messages which describe something about the source that changed. So this is a way for a source to say, I have changed in this way. So we'll send a message, an inform message, and that will have an identifier for the source and some kind of state. And then we can do the same thing that we're doing now. We can have patterns that match those changes, find functions to handle them or that care about them, call those functions, and instead of returning whatever they want to return, they will return transform messages. So transform messages are very much like the messages that I showed earlier. They have an operation, they have a target, and they have arguments. And a transform message is saying, here's how I would like you to change. So we have these two sides, right? Here's how I changed, and here's how I'd like you to change. And so I want to walk through how we can make Pedestal from these kinds of channels. So again, we're going to go through the whole process. We have a view, an event occurs. What we're going to do is take that callback, and when we run that callback, we're going to take the event and turn it into an inform message. So that message is going to tell us something about how the thing changed that we care about. So this is our inform channel in blue. And then we're going to find a function based on that inform message that cares about that and can transform that into a transform message on the data model. And instead of actually finding a function here, we're going to directly apply it to the data model. If we know the path to the thing we want to change, we know a way to automatically find the function that we're referring to, and we know the arguments, we can just apply that with update in to the data model. So we remove a step there. And then when we talk about the data flow portion of state transitions, we can do that with these same channels. So we can have an inform channel that tells us here's how the information model changed, and we have a function that we found which generates transforms, and those get applied to the information model. Once this is finished, we'll have the final inform channel coming out that tells us how the info model changed as we've gone through the entire data flow. And then what we can do is we can find here, just like our emitter in the previous example, we can find a function which will generate the transformations that must happen to the user interface. And then finally, this is just like our renderer, we can find the functions that actually make the changes to the user interface based on those transformations. And if you think about this, it's the same separation, except now we're using channels, and we've got fewer parts. So another advantage that this gives is that it allows us to we can encapsulate changes in widgets. So if we'd like to not do the manual message transformation and finding functions or manually handling transform messages by updating the UI, we can encapsulate that in widgets. And so in the application that we built, we could either write our own widgets. That was actually a nice way to handle it. Or we could have reusable widgets. And I don't know if any of you have looked at the work that David Nolan has been doing, like his example of the autocomplete field that he created. That's the kind of thing that if we made it aware of transform messages and inform messages, we could just use that in our application, as long as we have a sufficiently good way to customize it. And another thing to know about widgets is that they may not just be valuable for the UI. Maybe we could have some that help us with parts of the service. So that's pretty much it. Thank you. Check out Pedestal if you're interested. If anybody would like to talk to me about this, I'd be happy to talk to you. If anybody thinks this is a good or bad idea, just come and talk to me. I would love to especially hear people who think this is a bad idea. So are there any questions? Yes?
How does this future impact working with hires who have folks that are not skilled and we don't know their ability to just
Well, if I think we want to make some kind of API so that you could have JavaScript widgets that would actually plug into this. I don't think that's actually going to be a problem. We want to support that, definitely. Yes, Kyle.
So if I understand right, the key advantage of the current model is that almost all your logic sits in little functions that are very easy to test.
Mm-hmm.
You lose any of that by having them wired up with CoreAsync, where now you have to set up message flow to test your logic versus it's just a function that anybody can test for you.
You don't, because the functions themselves wouldn't really be aware of the CoreAsync stuff. So the engine is wiring up the functions, and the engine is responsible for creating like the pipeline that's going to run your code. So the functions themselves wouldn't necessarily need to be aware of CoreAsync unless you wanted to have a function that returned a channel, which is actually one of the advantages of this. You could have a function in your data flow that if you had a sufficiently fast like API that you wanted to call, it's much easier to write the straight line code that calls that API and blocks. And you could just return a channel that would then, when you read from the channel, it would get the result instead of returning immediately. So that's actually one of the advantages of this. The functions normally shouldn't have to know. Yes?
How does the replay functionality work? You talk about testing with replay. How does it actually work, and how do you change in this future mode?
I don't think it changes at all, because we still have messages that define all the changes that we're making, and we can store those messages and replay them later with a part of our application. I didn't really show that at all. Because we're sending data, sending messages to a renderer to render, we can actually record those messages and play them back through the renderer. And that is very helpful when you're making super complex stuff in the UI, and you have to maybe have like 5 people simulating, like acting on one thing. It's easy to, you can do that simulation one time, record the data, and then run it over and over again to get the rendering just right. But I think we'll still be able to do that kind of stuff. Yes? Sorry.
Does Pedestal provide any infrastructure for helping you get the code into the web worker?
It does, actually, yeah. But web workers are actually super hard to work with normally. You have to decide ahead of time which code is actually running in the web worker. And we added some support so that you can configure your application to say, here's the stuff that I want to run in the web worker. And then when you compile, it will automatically compile that stuff into like its own file and load it in the web worker. And there's even stuff for like making the going across the boundary, like the channels go across the thread boundary. Yep, but it is still a little bit hard to use. If you want to know about that, check out the tutorial. The very last section of the Pedestal tutorial has all the documentation for how to do that. Yes?
In the middle of the flow, where you've got a sort of loop where you like keep making changes to name model, how do you know when you're done?
So in the current model, we can actually figure that out ahead of time by looking at the inputs and outputs. We configure what are the inputs and what are the outputs of each function that we run. And so we can order them and then run them in order one time so we know we're not going to get in an infinite loop. In the new version, we would do like a fixed point. So we have to be careful. We'll have to be careful to just not run forever and maybe kind of throw some error if people do something wrong, right? But it'll be like a fixed point setup. Anything else? Okay. Yes?
How did the choice of Clojure make this project easier?
How did the choice of Clojure make this project easier? Well, the whole project, all of the ideas in it are based on like the ideas in Clojure. So it's kind of a hard question to answer because we wouldn't even have thought this if we weren't using Clojure. And so because we are so absorbed into those ideas, this actually feels kind of natural. So I guess that's the advantage, is that Clojure makes it feel natural. A lot of people think this is very confusing, but I think for people who are really into Clojure and doing stuff on the UI, I think that it is actually, it feels quite natural. Anybody else? Yes, in the back.
We're taking a look at all at web component specification.
Which one?
Web component specifications with W3C, integrating shadow DOM and some of these other forthcoming project technologies. And you talk about the widgets, and I'm wondering if they might be able to distill them down in terms of web components or compile them down to web components.
Yeah, we haven't looked into that in detail yet, so that's something that we're going to be doing in the future. So no, the answer to your question is no, I haven't looked into it. Okay, one more question and then we'll wrap it up.
Yeah, the difference between the two styles, so the older messaging
Yep.
style and the newer one, could you just spend a second talking about sort of the concerns between the two? Because it seems like there's a slight difference in the end result, right? So you're saying, here's how I want you to change.
Yeah.
You know, here's the thing that I'm going to apply. And then the other one seems a bit more like, I did a thing, there's something over here that's not with you.
Right. So actually, they're both actually the same. They just seem different. You're always in the first model. We are saying, here's how I want you to change. Sometimes we talk about it like, here's a change, react to it. But really, we're saying, here's how I want you to change.
You're still just mapping what function do I want you to run. Like here's that map.
Right.
And then go do it.
Yes. So I think what we're doing is we're being more clear about what the roles of each part are. So, all right. Thank you.